Okay, so we're going to be talking about exponential functions today, right? We're also, one of the ways we're going to learn about them is comparing them to some of the functions we've learned before. Okay, so we've actually already learned about, and we'll make a makeshift graph here. What's going on? Oh, there you go. Okay, so a little makeshift graph here. We've talked about functions that are linear, and a linear function is something that's a straight line. We've talked about things that are quadratic, so we get something like that in a parabola. And now, this one I don't have a tool for drawing, so you're going to have to bear with me while I do it by hand. We're going to talk about exponential functions, okay? We'll do that in red. And exponential functions look roughly like this. They don't move up and down, they just kind of go up and up and up and up and up. Okay? So the red one's kind of our exponential function. The first one, here, this is a linear function, okay? And linear functions are usually modeled by what we call y equals mx plus b. Do you remember that equation?
Yeah.
Yeah. We usually talk about it in that form. Our second one here is quadratic. Okay. It's quadratic. And quadratics are, again, they're usually written like y equals ax squared plus bx plus c. Do you remember that? We talked about this for a while, right? That's a standard form of that one. Okay, now an exponential function, which is our one in red head. Exponential is y equals, now they haven't really talked about it in your book, but we're going to give variables to a, b to the power of x. Okay, so these are three different types of functions. See how they are drawn differently when we graph them? It's important that we know the differences between all of them. Linear, for instance, it'll go up by the same amount every time. We go over, up. So say we're going over 1 and up 1, it continues that pattern the whole way, right? We know that. Quadratic, we're used to going over 1 and then kind of squaring it, right? Over 1, up 1. Go over 2, you'd go up something like 4, right? If we went over 3, we would go up what's considered to be 9, okay? Now, if you look at exponential, it's a little different, okay? In the first one, they went over 1, it changes 1. In the next one, over 2, and you multiply it by 2. So you're always constantly multiplying by whatever your last one was. So the idea of this is, let's say we went over a change of 1. Went over 1, up 1, okay? The next one, if our base term, it depends what our base term is. So let's say they've given us f at x is equal to base is 2 to the power of x. So we're talking about the number 2 right now, okay? So changes 1 in the first one. We then go over 1 again. Well, this time we multiply our old number 1 by 2. I should write that one nicely. Oh, that's not what I was looking for. Okay, so up. So our change was 1, went over 1, up 1. Our next change, we went up 1 before, so we multiply that by 2. So we actually end up going 2. And this one we went up 1. Okay. The next one we'd go over 1. Our last one we'd gone up 2, so we multiply that by 2, we go up 4. We go over 1 again, and it flies up. Last time we went up by 4, well, we multiply by 2, we go up by 8. It's constantly going up by more and more and more each time. That's what an exponential function does. Okay. And there's different types of exponential functions. Let's come out of the graph again here. A little makeshift graph. Whoops. Another one. Now, depending what our variables are, and in this case we were using f at x was equal to, we have three variables here. Okay, we have an a, b, and to the power of x. Okay. When they talk about a is initial value. So you'll start to get into questions about you know, you have so much, there's so much of a population somewhere, so maybe like 500, okay, and it's going up exponentially every year. It's going up by more and more and more. The initial value would be, what did it start at, the population? Or sometimes they talk about decaying. When matter decays, say there's something that weighs 500 pounds, that's its initial weight, and every year it loses half of its weight. It's a decay rate. So we'd start at 500, that would be A, our initial value, and then it gets cut in half, goes to 250, then cut in half again, 125, okay? B, if given many terms, it's usually considered a growth or a decay rate. Growth or decay, okay? And what they mean by that is you can have growth, which is the first one I drew, where it starts off really low, hits the number, and then starts taking off up to 1. Decay would be the opposite. It comes down, crosses, and then gets ever closer to the x-axis. Okay? This would be considered decay, and this would be considered growth. Now, my highlighter won't do it justice, but technically, this x-axis here with our growth and our decay rates, it's never going to touch them. Okay? And the reason for that is I want you to think of something hard to visually represent, but walking halfway to a wall. Okay? So let's say I jumped on another page here. You know, you're a guy and you're walking to a wall. Real happy guy walking up to the wall. And let's say, you know, you have a distance of, I don't know, 20 meters to the wall. Okay? So we're 20 meters away. And someone says, I want you to walk to the wall, but I only want you to go halfway every single time. We go, sure, no problem. So the first time we step out, how far do we travel?
10.
Travel 10 meters. Have we talked about this before? Okay. And then how much room do we have left?
10 meters.
Still have to go 10 meters left, right? So we split it. Still have to go 10. Well, that means I'm standing here now. Happy guy. Let's, I'm actually going to move him. Perfect. Good. So now he's there. 10 meters away. Now he says, well, walk halfway again. How far would we go? Okay. So now this happy guy is 5 meters away. Okay, well, 5 meters away. So he's got 5 meters to go. And they say, you know what? Walk halfway again. Now how far away is he from the wall?
2.5.
He's now 2.5. So our happy guy is getting closer. But now they said walk. I'm going to get rid of I'm going to get rid of this guy just so we have some uniform here. That was our first walk. We went 10. Alright, so we walked, he walked, he walked. 2.5. Okay, walk halfway again. Okay, well that means 2.5 is equal to 1.25. Very good. So we walk halfway again. So now we're at 1.25. Okay, now I know he's a human being, so his big fat head is looking like he's getting closer to the wall. Let's say he's there. And we'll say we want his center to be right at the wall. Well, if we say walk halfway again, well, we're going to be half of 1.25, which is going to give us, I think it's actually 0.75. Okay, so he's again walked halfway. And now our numbers are going to get smaller and smaller and smaller, right? But are we actually ever going to reach this wall? We're never going to get there. In other words, when we go back, we look at our dual pages here. Oops, not a page I wanted. Look at our 2 pages. That wall, think of it like the x-axis. Okay, we're actually never going to touch that x-axis, and this is like a decay rate. What's happened here? Let's get our magic creator. Oh, I can't use magic, unfortunately. What we're going to do here is, you know, we started by moving 10. Which is a big number we dropped, right? So we went from 20 to 10, dropped down really fast. That's what our blue one did. And then we went from 10 to 5, well, dropped down, not as fast. Then 5 to 2.5, still dropping, but not as fast. And then it slows down in the amount it drops, but never actually reaches the wall. It's going halfway, halfway, halfway. And it can go more than halfway. It can go a third or a ninth or whatever that fraction is, but it'll actually never reach there. Okay, so that would be considered like a decay rate. And what we mean by that is our decay rate in this case would be B would be a half in that one. Okay. So that would be our decay rate. And then, well, X is our exponent, but they also usually represented as the number of periods or the number of times something happens. Okay, so we'll call it like number of periods, or number of times something happens. Okay, so if you take a look at this now, we got what all of our variables are talking about. And what we're going to try to do is we're talking about growth and decay. So growth, I'm going to quickly touch on. Growth is technically 1 plus whatever the GR, we're going to call that growth rate is. Okay? And decay is actually 1 minus whatever the decay rate is. And they're usually given as percentages. Okay? So growth rate is our GR. Say it was a growth rate of 5%. Okay, remember this is our B. B is equal to 1 plus GR, B is equal to 1 minus DR. Growth rate of 5%. Well, what's 5% as a decimal? 0.05. 0.05. Alright? And we got to add it to 1. So our B value for that growth rate would be 1.05. That would be our B value in our number here. Okay? Say we had a decay rate. And the decay rate was to go down by 10%. Well, what's 10% as a decimal? 0.1. And we got to make it our B value. It's actually 1 subtract 0.1. So what's our actual B value in this one? 0.9 is our B value. So growth rate's pretty simple to look at because you kind of go 5%, 0.5, 1.05. Decay rate's actually just the number has to be less than 1. Okay? And that's what you're going to notice. Growth has to be greater than 1. Okay, we'll put that on the side here. Growth has to be greater than 1, where decay has to be less than 1. If the B value is greater than 1, we'll get a graph that goes upwards. If it's less than 1, we'll get a graph that goes downwards. A is the initial value, so what they're talking about is essentially the y-axis. Where did it start at? Okay? We usually refer things to time, and then x is the number of periods it happens over. Maybe it's over 50 years, 50 cycles, or something like that. All right. Another way we can tell if something is exponential is sometimes they'll give us tables. Okay. Well, we've talked about something called first differences before, and first differences talk about how to tell if something's linear. So what we'll need is an x value that's consistent, that constantly goes up by the same. What we have here, our x values are all going up by 1 the entire way down, right? First differences is we just take one of the numbers and subtract the other. Okay, that's the idea behind first differences. So, for instance, I do this, and I get 2, subtract 1. I'm taking the 1 from the bottom, subtracting 1 on top, I get 1. Bottom from bottom on top. We have to keep that same pattern when we do first differences. Okay, 4 subtract 2 is 2. 8 subtract 4. Well, that gives us what? 4. Okay. 16 subtract 8. 32 subtract 16. Yeah. 64 subtract 32. 128. Made a really big table here. Subtract 64 equals 64. 2, 5, 6 subtract 2, 8 equals 2, 8. And finally, 5, 1, 2 subtract 256 equals 256. Are all those numbers the same? No. So first differences did not work. Second differences. That's how we tell if something's quadratic. Do you recall this at all? Yeah. We subtract these values, okay? So 2 subtract 1. 4 subtract 2. 8 subtract 4. 16 subtract 8. 32 subtract 16. Yeah. anything really happening here? Are these going to be the same? Sorry, are these terms or second differences all going to be the same? No. All the numbers are constantly changing, right? 256 subtract equals 120. So the second differences are the same. We don't have a linear relationship. We don't have a quadratic relationship. Now this is called exponential ratio. Okay, we find the ratios of things. So I'm going to call it exponential ratio. We do the same thing as we did before, but instead of subtracting, we divide. Okay, so I'm going to take those first two terms. 2, so we'll call this the first step. 2 divided by 1 gives me what? 2. That's right. Here we get 4 divided by 2. So 4 divided by 2 gives us what? Well, that works out good. 8 divided by 4. There we go. 16 divided by 8. Okay, so you're noticing a pattern here. The ratio, we'll keep it going here, 32 and 16. The ratio for all of these ends up being the same. When the ratio for all of these ends up being the same, that means we have some type of exponential function. Okay, so this is another way of telling 2, and finally 5, 12 divided 2, 6, 2. Lots of writing for me. So our exponential ratio, the number 2 is always the same. So we know we have an exponential function when looking at this. So we test these things out. Now I might have chosen to do exponential ratio first because I don't have to build up to it. So I could start off with that, and I might not get it. First difference is we got to try linear first before we can try quadratic. Right? We have to do first differences, then second differences. If we think it's exponential, we could always start off with that because it's not a building. Okay? But that's how we do it from a table. Okay, exponential functions again. Right? We have a graph here, scale of 10, and we have an exponential function. So what I want us to draw your attention to is y equals, and remember we had a, b, and to the power of x, right? Now, 4 is actually which of these? A, B, or X?
B.
B, that's right. So what do you think A is in this instance?
1.
Yeah, that's right. It's 1. So the initial value is 1, is what they're telling you. Initial value is actually our y-axis. Okay. And another way we can figure this out, and I'm actually going to take this equation and work with it, y is equal to 4 to the power of x. Well, our y-axis is when what is 0?
4.
Well, not 4, but the which variable is 0?
X.
X. So if we're trying to find a y-axis, we look at when x is 0, which means we're going to get y is equal to the power of 4 to the power of 0. Y is equal to 1, which is the exact same as our a value, right? So what they're saying is the initial spot, and there's a paragraph drawn, is at 1. Okay, so technically we have a point at 0 and 1. That's where we're starting from. Okay, and now from there, what we do if we got to plot this graph, we put in our x values. Well, in this case, I have numbers across here. It's not even that great of a graph, I just realized. Say we're at x at 1, okay? We're looking at y is equal to 4 to the power of 1, which is going to give us a y value of what?
4.
4. So when x is 1, which is really close over here, we're looking at 4. When x is 2, 4 to the power of 2, what are we getting? 16. So when we're at 2, we're at 16. Okay, let's jump up to say 5 here. 10. Jump up to 10. When 4, we jump to 10, it's going to take off too much. I drew the scale funny. Anyways, you kind of get the idea that we're going to be looking at something like this. Okay, here's our initial value, and this guy is going to just take off straight up, especially because we spreaded this out by 10s. I should have done this by 1s and that by 10s, which we can do. Let's say in this instance, let's just scratch out our zeros here for now. Okay, let's pretend that this is actually going up by 1s in our x value, just so that we can get a better idea of what's going on in this graph. Okay, so when we said it was 1, 1 was actually at the number 4, which is still relatively low. 2 was 16. Okay, let's talk about 4 to the power of 3. So y, when x is 3, that give us? Well,
64.
that's right. We're looking at, again, it's going to be 64. So when we're at 3, we're all the way up here already at 64. Okay? So we look in reference to our graph, and what about when we're at 4?
256.
Yeah, way off. Again, we barely went anywhere, and we were going up by tens, and this just takes off. Okay? That's what this type of graph does. Our y-axis, or y-intercept, sorry, is at 0 and 1. What about when we're talking about the number, and this is why we need to know our exponents, what about if we're talking about y is equal to, and x is negative 1? Well, that's going to give us y is equal to 4 to the negative 1. How do I make that a positive?
1 over 4.
That's it. Is 1 over 4. So it's a quarter of the way. Now, really hard to represent, especially on a graph of this scale. But we're at negative 1, and again, let's pretend these are going over by 1. So let's get rid of these zeros here for the argument's sake. We're at a quarter. What about when x is negative 2? We're talking about y 4 to the power of negative 2. We make it a positive. It's 1 over what? 4, 2, which is? What's 4 squared? 1/16. An even smaller number. Do you see that idea? Now, it's very small, but again, it's never going to touch our x-axis, correct? We're going to stay very small. We'll get to our y-intercept, and we take off and head up. That's the idea of this graph. Now, they're going to talk about the domain and range of this. Okay, so maybe they want to know what's the domain of this graph. Let's take a look at the whole thing. Domain. Well, our domain is we know x is going to touch all real numbers. Is there any limit to how far left and right x can go? No, it's just going to go on forever. Y, our range, though, is a bit of a different story. Of course, y does touch all real numbers, but there is a restriction. What does y have to be less or greater than? Y has to be greater than, and it's not equal to, because it never touches 0. Y is greater than 0. That'll be our domain and range for this question. We've sketched our graph. It looks roughly like that. State the equation of the horizontal asymptote. What is the horizontal asymptote here? Do you know what they're talking about? What line will it never touch?
The x-axis.
Our horizontal asymptote is the x-axis. So in other words, our equation is y is equal to 0. That's the horizontal asymptote, or HA. Okay? It will never touch 0. Now, in my second equation here, I know I drew it in, we just didn't really talk about it yet. Here's our second equation. Again, it's the number 3, so a little different. No, I don't want crayon. Pen and green. Okay. Now, this idea, and we'll scroll down here so we can see it. It's 3 to the power of x minus 10. So let's talk about that idea. Y is equal to 3 to the power of x minus 10. Well, when x is 1, what do we get? 3 minus 10. Our y value is actually negative 7. So when I go to draw this, it's actually down here at negative 7, my y-intercept. Okay, it's a little different. Okay, again, it will take off the same way the other one did. What about when it's 2? Y is equal to 3 squared minus 10. What's 3 squared? 9 minus 10 gives us negative 1. Okay, well, again, we're talking about negative 1. So we moved over 1. We're at negative 1, something like that. What about 3 to the power of 3?
27.
We got minus 10.
17.
Yeah, we get 17. So it's going to start to take off too. $17. Okay, and then what about 3 to the power of 4? Is that 2? Oh, sorry, I did make a little error here plotting these points. Take a look at the points I put. I actually put them in the wrong spots here. My first point, 3 at 0, which is our y-intercept, I only did 1. 3 at 0 should have actually been y1 minus 10. Should have gave me negative 9, right? Negative 9, negative 7, negative 1. So we should have been at negative 9, negative 7, negative 1. At 3, we're at what? 17. And at 4, what number were we looking at?
81.
81. right? Oh, so way up there again. So again, this is taking off just like the last one did. Now, the only difference here is of our negatives. Okay? What about if I'm talking about y is equal to 3 to the negative 1 minus 10? Well, that's going to become what fraction? 1 over 3 to the power of 1, which is still 3, right? Minus 10, we're looking at 9 and 2/3, right? And then say we do y 3 to the negative 2, so we move over another. Well, that's going to give us 1 over 9, right? Minus 10, which is give us 9 and 8/9, right? So we're constantly getting closer and closer to what number? 10. Do you think we'll touch 10? No. We constantly get closer and closer to this 10 here, which I'll put it in green highlighter. So our horizontal asymptote is going to be what number here? 10. Yeah, now it's a huge highlighter for number 10, I know. But we're supposedly getting closer and closer without ever actually touching the number 10. So it's a flat line, and then it takes off again. The domain and range for our green one, what's our domain? X is every real number. What about our range?
Greater than 10.
Y has to be greater than 10. We knew our y-intercept was where? We figured it out at negative what?
10.
Not 10, what?
9.
9, right? It was at negative 9. So we still did a lot there. We can actually shift these exponential functions up and down. And remember, to see how that was, that's kind of like a k-value. The k-value moves the entire graph up and down, just like we did with our sine waves, just like we did with our quadratics, right? It moves the entire graph up and down.